All right, hello everybody. We are working on activity 7 of the Unit 2 review. It has the Hulk hand on it if you were looking for the picture that corresponds with it. And activity 7 is all about writing equations for functions and still identifying those key features of graphs and looking at graphs of real world situations. So let's go ahead and get started. All right, so in your document, this should be changed because this is a question we pulled previously. So it says a weight of 32 ounces stretches a spring 16 inches. So how many inches does the spring stretch per ounce of weight? So I've got a spring, and there's a weight pulling on it, and when it pulls, it stretches it from its original length 16 inches. Right? Yeah. So it's it's increased by 16 inches. So if it's a weight of 32 ounces and the increase is 16, what's the relationship between there? What we can say is we can divide these. Or actually, let's write it as a fraction. So 32 ounces makes a stretch of 16 inches, which means 1 ounce. If I wanted to know how much does 1 ounce stretch, I can divide this and divide both of these by 32, because 32 divided by 32 gives me 1 ounce. So that's going to give me about 0.5 inches. So every ounce stretches that spring by ½ an inch. So we're going to write that 1 ounce stretches the spring. I don't know why I have string on the brain. ½ an inch. Okay, so 1 ounce stretches the spring ½ an inch. So I want to write an equation based on that describes the distance it stretches and the weight attached to it. So how much? So when we write this, the weight is what is controlling the distance. So that means that the distance is dependent on the weight. So we're going to make distance our dependent variable, and our weight's going to be independent. So that weight is causing the spring to stretch ½ an inch. So how we're going to write that is by 0.5 and then times the weight. Okay, it says use the information to show that your equation is accurate. Well, if I plug 16 in for the distance, and I plug 32 in for the weight, half of 32 is 16, so 16 equals 16 is a true statement. Okay. Part C, how much will the spring stretch for a weight of 54 ounces? And we're going to use this function or this equation we wrote. So all we're going to do is change the weight to 54. Okay, well what's half of 54? Well, half of 50 is 25, half of 4 is 2, 25 and 2 is 27, so the spring should stretch 27 inches. Okay. Alright, what if the spring is stretched 100 inches? How many ounces is the weight that's attached to it? So now we're going to plug the 100 in for D and solve for W. So what we're going to do is we're going to divide this by half. And a lot of people are going to be tempted to say, okay, half of 100 is 50. But we're not doing half of 100. That would be 0.5 times 100. We're doing 100 divided by half, or how many halves are in 100. So if I took 1, there are 2 halves in 1. There are 4 halves in 2. So we're basically multiplying by 2. Also, if you use a calculator, which you're more than welcome to do, there are 200 halves in 100. So the weight is 200 ounces. Units are kind of important here. Okay, so let's make sure we keep that. All right, number 2, a spring stretches 8 inches for each ounce of weight. So we're going to write the function first. So we're going to still use D and W. So D is going to stretch 8 inches for 1 ounce. So that's our common difference. Every ounce we add, it's going to add 8 inches. So we're going to do 8W. D equals 8W. If you were to graph this function represented by this situation, what would be the reasonable domain? So let's talk about weight. You're not going to have a negative weight, so the smallest you can have for your weight is 0. So 0 ounces is the smallest weight. Negative weight doesn't make sense. And then as far as the largest weight goes, we don't know at what point the spring would break. We don't have a limit to how much we can put on the weight. So we could put, I don't know, 1,000,000 ounces. We don't know. We don't know. So what we're going to say is, because there's no limit to how much weight we can put on, it would be all numbers that are greater than or equal to 0. So our domain is going to be that x is greater than or equal to 0, because we don't have a limit to the weight we can put on. Okay. All right, C, identify one data point, WD, that would lie on the graph of the function and interpret the meaning of the data point in terms of the context of the problem. Okay, so if we were to graph this, when we have no weight, the spring doesn't stretch, so it would start at 0, 0, and then for every ounce of weight, it would stretch by 8 inches. And this is just a quick sketch. And we can assume that if we put like 1.5 ounces, it would stretch up 12 inches, or if we put half an ounce, it would stretch 4 inches. So we can assume that this would be a continuous graph. So we just need to pick a point on this graph that we just made up. So what I would do is I would do D equals 8W. I would take our equation. I would just pick a random weight. So let's say we put a 4-ounce weight on there. And that would mean that when we multiply this, D would equal 32. So we could have the point 4, 32. Now again, you can choose any W value or any input value, and that's fine. You cannot choose a negative value because a negative weight doesn't make sense, but you could choose any other value, any positive value you wanted. So here's one that I picked, and if I want to interpret the meaning of this point, we're going to say that a 4-ounce weight would stretch our spring 32 inches. And that's it. And you could pick another data point. I don't care what your W or your X value is. Just make sure that you substitute it into the equation and get the correct Y value or the correct D value here. And then any point would be interpreted the same way. It'd be this many ounces stretches at this many inches. Okay. Alright, so let's look at number 3. And I like these graphs. They make me happy. I don't know why. I like quadratics. Okay, so we have, suppose that the height of an object after x seconds is given by f of x equals 72 minus 2x squared as shown in the graph below. What is the reasonable domain of the function? So, if you look, you cannot read the tick marks on here. You can't tell what the what it is or what the numbers here are. I'm not sure if that's done on purpose or not. So let's talk about what this graph is measuring real quick. It's measuring how long it takes for this object to fall to the ground. So this is height 0. So let's look at something really quick. Why don't I try to figure out what that point would be? If my height is 0, we're going to do 0 equals 72 minus 2x squared. Okay, so let's get this x positive. Let's make this 2x squared. Let's add it to each side. 2x squared equals 72. Now again, we're trying to get the x by itself. Let's divide both sides by 2. And we get x squared equals 36. Okay, those of you that are in semester-long algebra may not have gotten to this point yet. Those of you that are in year-long algebra, this is where we were leaving off if you were in my class. So we're going to take the square root of each side to cancel out that x squared. And we should be left with x equals positive or negative 6. Remember, when you take the square root of something, positive 6 times positive 6 gives me 36. But so does negative 6 times negative 6. So all square roots, with the exception of the square root of 0, all square roots have two possible solutions, a positive and a negative. So your solution, so x is going to equal positive or negative 6. But let's look at this real quick. Here is my y-axis where x equals 0. We're to the right. So what we can assume is that this is 6, positive 6, not negative 6. Also, if you're measuring how long it takes something to fall, does a negative time make sense? No, it doesn't. So we're going to just use the positive value. But those of you that have gotten this far, I just wanted to kind of throw that back out there that, hey, when you take the square root, you should get a positive and negative answer. So I just wanted to throw that back out there. And then for my kiddos that are looking at this that were in semester-long algebra, you haven't seen this yet, and that's okay. I just want you to be aware that it's out there. Okay. So going back to the original question, what is the reasonable domain? So again, negative time doesn't make sense, so we're starting time at 0. When the object hits the ground, there's no reason for me to measure any time after that. It's going to stay on the ground forever until someone picks it back up. And if we're talking about this function, if we were to continue graphing this function, my height's going to be less than 0, and that doesn't make sense either. It's like a softball just like driving down into the Earth's crust. That doesn't really apply here. So we're just measuring from 0 to 6 seconds. So my domain is that x is between 0 and 6 seconds. All right, B. What is the range of the function? We're going to do the same thing. We are measuring from the top of our graph all the way down to the bottom of our graph. So when our ball hits the ground, or whenever our object hits the ground, the height is at 0. So the lowest height is at 0. What was our starting height, though? It looks kind of hard to tell, but if we go back to this function and plug 0 in for x, so let's do that. Because we're measuring at time 0. Okay, so 0 squared is 0, and 0 times 2 is 0, and 72 minus 0 is 72. So our height, our highest value is at 72. So what's the reasonable range? The lowest our height is at 0. The highest our height is at 72. Okay. what is the y-intercept of our function? Well, that would be right here, and it would be at 0, 72. Because again, we just plugged 0 in for x and got 72 out, so that would be our y-intercept. What does it represent? That is the starting height of our object. You could also say it's the height at time 0. Okay, the x-intercept is where it crosses the x-axis. That would be here at 6, 0. And what does that represent? Well, at 6 seconds, the height is at 0. So we could say the ball hits the ground. I keep saying ball. We don't have any idea what it is. Our object hits the ground at 6 seconds. Or we could say at 6 seconds, the height is 0. Alright, Lori says that the domain of the function is all real values of x. Use the information from the function in the graph to show that Lori is incorrect. Okay, so remember, our domain measures time. So let's write that down. Okay, domain measures time. All real values of x includes negative numbers. Negative numbers are real values. So if we think about this logically, it doesn't make sense for us to have negative time. Once time stops, you don't go backwards. This isn't a Doctor Who situation. This isn't a Doc Brown situation. This is we don't have access to time travel yet. It's coming, but we don't have access to it yet. Once we have time travel access, then we can use all real values for time problems. But until then, we don't have access to go back in time, so we cannot use negative time as a domain. So we're going to say all real values means we include negative x values and negative values don't make sense when measuring time. Okay. Whew, my handwriting is getting messier and messier, but that's okay. At least it's getting up there. Alright, number 4. The half-life of a radioactive substance is 1 hour. If you begin with 800 ounces of a substance, how many hours does it take for 50 ounces to remain? So what's happening is we have a half-life means that for each half-life, half of your substance dies off. So in this case, after 1 hour, half of our substance would die off. After 2 hours, another half would die off. After 3 hours, half of what's left would die off. So what's happening is at time 0, we'll make us a little table. At time 0, or at 0 half-lives when we start, we have 800 ounces of a radioactive substance. After 1 hour, which is a half-life, after 1 hour, this decreases by half and we only have 400 ounces remaining. After 2 hours, that cuts in half and we have 200 ounces. And so on and so forth. And at 4 hours, we have 50 ounces remaining. Whew. And I'm sorry, I promise I don't have coronavirus. I spent some time outside with my son, and the pollinating has begun. And so my allergies are off the wall right now. So I'm sorry if you hear me sneezing and coughing and all that good stuff. I promise I'm not dying. It's just allergies. Okay, Number 5, the graph below represents a radioactive decay situation. What is the original amount of radioactive substance? And explain how you know. Okay, so just looking at this graph, we have 20 and 30. 1, 2, 3, 4, 5. So there's 5 spaces in between, so this would be 22, 24, 26, 28, 30. And this point is in between 24 and 26, so we're going to say, I would safely assume that's 25 ounces. How do I know? Well, why did I pick this point and not some random point out here? We're looking at time 0, and we're also, that's when that would be the original amount. That's our y-intercept. And our y-intercept, let's go ahead and be correct with it, is 0.25. Okay, what's the reasonable domain and range? So let's talk about the domain for a second. Again, we're measuring domain and time. And as this is dying off, if we look at our graph, it looks like it finally touches 0. But if you're cutting something in half, let's say you have 1 ounce. Well, if you cut it in half, you're down to ½ an ounce. If you cut it in half, you're down to 1/4 of an ounce. And you can keep cutting it in half. And eventually, it'll be a microscopic amount, but it won't go away because you can still cut it in half forever. So this line is called, this graph is getting closer and closer and closer to your x-axis, but it's never going to actually touch it. It will never actually equal 0. It's always going to get closer and closer and closer and closer and closer. Like if you were to graph this on Desmos, you could keep zooming in and seeing like a little bitty bit of space between the line or the graph and the x-axis. So the x-axis here is called an asymptote. And that is a line that we're getting infinitely closer to, but not actually ever touching it. Let's go back to domain, because that's really going to help us with range. So since it's never actually going to run out, it's going to keep cutting in half forever and ever and ever. But again, negative numbers don't make sense here. This is still time, so we don't have negative time. So we're going to say that x is greater than or equal to 0. It gets close to 0, but it never actually touches it. And then our range, the lowest amount, we're never actually going to touch 0. So we're going to start that 0 is less than y, but because it won't actually ever touch 0, it's just less than, not less than or equal to. And the most amount of substance we're going to have is 25 ounces because that's when it starts dying off. So that's our maximum. All right, so there's our range. All right. Okay, so let's go on to C. It says, identify and interpret the absolute minimum and maximum values of the function. So the absolute max, what was the most amount of substance we had? We had 25 ounces of our substance. Okay. So that's the highest amount of our substance. And as far as our minimum, we really don't have a minimum. It's getting closer and closer and closer to 0. I don't think we can call that our minimum. I mean, that's the number we're getting close to. In calculus, that's called a limit, but I don't think we can actually call it a minimum. So I would say that there is no minimum, but it gets infinitely closer to 0. All right, 6. This one's going to be very similar to the half-life. Kind of, sort of, but not quite. So in this situation, Barney has a sheet of paper, and he's going to cut it in half, and then throw this half away. And then he's going to cut it in half and throw this half away. And then cut it in half. And you get the idea. Yeah, you get the idea. So, yeah, we get the idea. Okay, so that's what's happening here. When he doesn't cut it at all, he has 300, whatever the area is 300 square inches. Had to read that. After he cuts it in half once, it'll be 150 square inches. Cuts in half again, it's 75 square inches. And then we have 37 and a half. And then we have, I'm just double checking before I write the wrong thing down, 18.75. Okay, so how is this similar to the half-life of a radioactive substance? Both of these are decreasing. They both decrease by half of the amount. We could also say by 50%. Okay, so C, would the graph of this relation be continuous or discrete? Well, let's look at the half-life real quick. And this makes sense. Half-life would be continuous because it's, if you think about it, it's not, okay, 2 years it cut in half, boom, it's gone. Or 1 year, boom, it's gone. 2, boom, it's gone. It's slowly decaying, and by the time 1 year rolls around, half of it's decayed. And by the next time that by the next year, half of it has decayed again, but it's a gradual decay. Whereas here, you're cutting a piece of paper and throwing it away. It's not gradual. It's boom, 1 cut, I've got half. Boom, 2 cuts, I've got half. There's no 1.5 cuts. You can't cut it 1.5 times. You either cut it once or you've cut it twice. So this would be a discrete graph. And that's, we can just say it's not a gradual decrease. It's an instant decrease. You can also say there's no decrease or no change between 0 and 1 cuts. You don't have a half of a cut. A half a cut really is still a cut. So, yeah. So there's no change in between cuts, whereas with the radioactive decay, it's a gradual change. By the end of your half-life, half of your stuff has decayed. But if you were to measure it at some point in between starting time and the first half-life, you will have less substance. It's a gradual dying off. Okay, D, describe how the reasonable domain in this situation is different from the reasonable domain in radioactive decay. Here, again, we said there's no half cuts. I can't do like 0.278 cuts. You either have no cuts or you've cut it once. So in radioactive decay, we had all real numbers greater than or equal to 0. Here, because this is a discrete graph and we're not going to have anything between 0 and 1, we're just going to use all whole numbers. Our domain is going to be all whole numbers, and that's because this is discrete. Because you can't have a half a cut. It doesn't make sense in this situation. Alright, E, identify the y-intercept. So I don't have a graph to look at my y-intercept, but your y-intercept is the y value when x is 0. So our y-intercept is going to be this point here, 0, 300. What does it represent? The paper was 300 square inches, or inches squared, before any cuts were made. Okay. Identify the absolute maximum, and what does it represent? Again, absolute maximum is 300 square inches, and it's all, we can put it right here. This is the same thing. So the paper was 300 square inches before any cuts were made. So we can also talk about how there is no, or this is our maximum value, because once you start cutting, it's only going to decrease from here. Okay, so this was kind of a lengthy video, but it was also kind of a lengthy packet. And it also was very explanatory heavy. It wasn't really a something I could just say, okay, here's how you do it. This is a dissecting the problem and saying, okay, this is what this piece means, and this is what this other piece means. So again, I hope it was something that was helpful. If you have any questions, feel free to email me or your teacher, or you know, anybody that can help you with math. Feel free to email them and ask them about it. So thank y'all so much for your attention. I hope y'all are having a good day, and I will have another video for you soon. Bye!